This video is all about how atomic bombs work. The first nuclear weapons developed as part of the Manhattan Project, which include the Trinity device tested in New Mexico and the two bombs dropped in Japan in World War II. The term atomic bomb itself isn't really used anymore because it's inaccurate, but it was widely used back then, so it still makes sense in a historical context. Check this out. This is the map of the video. These are all the things we will look into. In the big picture we have a physics side of things where we'll explore the physical principles of nuclear fission. And we also have an engineering side of things where I will talk about how these principles were used to build machines, or bombs in this case. First, I will give a short introduction to the atomic nucleus, followed by the fundamentals of nuclear fission, and then some more details about energy release and how to create a chain reaction. While all of these effects happen at the microscopic or quantum level, on the engineering side of things we will deal with effects on our macroscopic scale. We start off with the concept of critical mass and then discuss the two designs used, the gun design for the uranium bomb and the implosion design for the plutonium bomb. Finally, there is a short chapter about atomic bomb effects. So let's get to it. And as this is a video about nuclear physics, Yasu Elina. Early on in the 20th century, we've learned from experiments that atoms, even though their very name means indivisible, are actually very much divisible and are made up of even smaller particles. The negatively charged and low mass electrons can be found in the atomic shell, which defines the size of the atom. The nucleus is in the center of the atom and is very small. The shell is typically 100,000 times larger. But the nucleus carries almost the entire mass. It is made up of two types of particles: the positively charged protons and the neutrons, which are almost identical except that they carry no charge. An atom normally has the same number of electrons and protons, so they are electrically neutral in total, and a slightly larger number of neutrons. There are two different forces competing within an atom. First, the electromagnetic force attracts the negative electrons towards the positive protons, so it is binding the shell to the nucleus. Also, it means that the protons within the nucleus, because they all have equal charge, repel each other. So how can there be a nucleus in the first place? Well, this is where the second force comes in, the nuclear force. It is related to the so-called strong force, and as the name suggests, it's rather strong, but it only has a very limited range. This means that the protons in the nucleus can latch onto a neighboring neutron, which kind of form a buffer between protons, so that this nuclear attraction can overcome the electromagnetic repulsion. And you can have a nucleus. However, this is always a fine balancing act and means that nuclei can also become unstable, which will become rather important later. An atom can have a different number of neutrons. This is called isotopes. Elements that only differ in the number of neutrons. They behave identically chemically and only differ in mass. There are only a few stable isotopes per element, and the rest are unstable and will decay, mostly by giving off alpha or beta radiation or emitting neutrons. So in the long run, only stable isotopes will persist. Nuclear fission is the process often colloquially called splitting the atom. It basically means that one larger nucleus is split into two smaller ones, plus some additional stuff we'll get into soon. A simple picture of how fission works goes like this. An unstable nucleus can go through oscillations and deformations, leading to an elongated form that can take on a peanut shape, which will then break into two parts as the longer-ranged electromagnetic repulsion overwhelms the nuclear force. In fact, drops of liquid can show a very similar behavior. This process can occur naturally, which is then called spontaneous fission, or it can be triggered artificially. All you need to do is transfer a given amount of energy into a nucleus, and the best way we have found to do that is to just shoot another neutron at it. Because, as we said, neutrons are electrically neutral, so they are not repelled by the positively charged nucleus, and therefore it is way easier to get them inside. They also bring energy in the form of kinetic energy, so all we need to do is shoot a neutron at a nucleus and bang, fission. Yes, in principle, but it is a bit more complicated than that. And that's because every process we're talking about here is governed by the laws of quantum mechanics. So there's always this fundamental randomness involved. All we can do is give the probabilities for certain things happening, and these are given as so-called cross-sections. A cross-section is actually an area, and the idea is that if you want a collision to happen, what you're really trying to do is hitting a target. The larger the target area, the likelier it is to hit. So in this sense, we can use an area to give a probability. So when shooting a neutron at a nucleus, it could simply just pass by, or it could be deflected, or even reflected, or it could just be absorbed, or it could actually trigger nuclear fission. All of these outcomes have a given cross-section depending on how likely they are. And as any material consists of an unimaginably large number of atoms, these atomic probabilities will manifest as statistical outcomes. The electrons in an atomic shell are bound by the electromagnetic force. The energies with which electrons are bound end up being in the range of some electron volts, or eV. Essentially, all of chemistry is determined by what the outermost electrons in the shells do. So all chemical processes, including a dynamite explosion for example, can at most release some eV per atom. The force holding the nucleus together, however, is the nuclear force. And when you do the calculations, you get much higher binding energies. These are in the MeV range, so any process removing particles from a nucleus can free an energy of some MeV. Now, I will not tell you what exactly an EV is and how it's defined, because that would give you no real insight, it would have no meaning to you. But I will tell you one thing. The M in MeV stands for mega or millions. So the simple conclusion is, if you make an explosion happen based on a nuclear process instead of a chemical process, it will be 1,000,000 times more powerful. And as soon as people realized that, the race for the atomic bomb was on. In what form will this energy be liberated in a nuclear fission? Well, mostly kinetic energy of the fission products and neutrons, but also photons, so light. Okay, let's go back to this MeV figure for nuclear fission for a second. The thing is, an MeV is only large in terms of atomic scale. So if you get just one MeV from a single atom, on our scale that is minuscule, it wouldn't even register. Only if a large number of atoms take part in the reaction, if you get the MeV many times, then we're talking dynamite times 1,000,000. It turns out there are some isotopes where this can be made to work, where a neutron capture causes fission, splitting the nucleus into two smaller ones and setting free energy and ejecting an additional 2 to 3 neutrons. And that's the kicker. Each of those neutrons has a chance of setting off the next nucleus, which in turn releases more neutrons, which set off more fission events, and so on and so on and so on. So for a short time, this creates an exponential runaway process called a nuclear chain reaction. So within just fractions of a second, this material undergoing nuclear fission will heat up and expand and explode in a violent burst of energy. And that is the essence of what a nuclear fission bomb does. It was discovered that this entire process could be realized with two isotopes, uranium-235 and plutonium-239. Uranium-235 only exists in trace quantities in a naturally occurring uranium-238 and must be enriched to be of any use. Plutonium basically doesn't exist on Earth at all and must be artificially created in a reactor first. Alright, so we've learned that on the atomic scale, what we need to do is start a chain reaction with fission setting free more neutrons, which then in turn cause more fissions and so on. Obviously, for this to keep going on, you need a certain amount of material because you need a large number of atoms that can take part in this chain reaction. This amount of material is called the so-called critical mass. And it depends on the density of the material and the cross-sections for fission and the other processes, and also how many neutrons are liberated by each fission. For reference, the critical mass of uranium-235 is 46 kg and the critical mass for plutonium-239 is 17 kg. This is just the minimum number though, so you always want more than that to get a longer running chain reaction and hence more energy output. Note though that just having the critical mass is not enough to get a nuclear explosion. You also have to set off the chain reaction first with some device that injects neutrons into the material, which is called the initiator. Just having the critical mass in this sense is only arming the nuclear bomb. Generally speaking, having a critical mass of a fissile material is kind of a hazardous situation though, so you want to assemble a critical mass and trigger it at the same time. Otherwise, you risk some random stray neutrons setting off the bomb prematurely and just giving a very low yield pre-detonation. One more trick that the engineers came up with was using a tamper. A tamper is a material around the critical mass with a high cross-section for reflecting neutrons. So you would stop a lot of neutrons from leaving the critical mass and bounce them back inside for another go instead. Additionally, in the moment of explosion, the tamper would press against the expanding material and hold it together for just a bit more for some extra energy output. Okay, so this name is no joke. The idea is to fire one subcritical mass at another subcritical mass, literally inside a naval gun. The gun had to be long enough so that the assembly would happen at a sufficiently high speed, or short time, and the entire bomb would still have to fit inside the cargo bay of a B-29 bomber, the plane that would be used for delivery. So they simply took the firing mechanism of a naval gun and put uranium inside and built a bomb around it. Pretty much, yeah. Critical mass and tamper size, etc. dictated that it had to be a 6.5-inch gun though, which was not a standard caliber, so it had to be custom built. It was also modified from a standard gun so that its weight would be reduced by sacrificing durability. Because in contrast to a regular naval gun, which had to survive being fired thousands of times, this gun would only have to be test fired a few times and then fired just once in operation. The gun simply fired a subcritical ring which would fit around the subcritical target cylinder, assembling a critical mass and triggering the initiator. You can see in the schematics of the gun bomb that the target mass is surrounded by the tamper, which was originally supposed to be made of beryllium because of its excellent neutron reflecting cross-section. Until they figured out that just a single bomb would use up all of the beryllium available in the entire USA at that time. So they used tungsten carbide instead. Initially, both the uranium and the plutonium bombs were supposed to work like this, but it turned out it wouldn't work for plutonium. Because the assembly time, the time it took for the critical mass to be fully assembled, simply was too long. Yeah, so firing that two masses together, literally with a gun, was too slow. And the reason was that with a plutonium-239 bomb, you would inevitably get some plutonium-240 into the mix from the production in the reactor. And plutonium-240 has the unfortunate feature of going through spontaneous fission a lot. So discharging a lot of neutrons, which is an unwanted initiator that just can't be turned off. It's almost a guarantee for a fizzle. And this almost upended the entire plutonium program of the Manhattan Project. But rather, in 1944, it was decided to focus all resources on making another bomb design work, the implosion design. This ended up being used in the Fat Man bomb and was considered so experimental and precarious that the project decided on first doing a live fire test in New Mexico, the so-called Trinity shot. And the basic idea of the implosion design is not to bring two subcritical masses together as with the gun design, but rather take one larger subcritical mass and compress it to crush it until it reaches critical density. This would require an extremely symmetrical explosion in all three dimensions, precisely triggered and synchronized. In the end, they developed a concept based on so-called implosion lenses, shaped explosives with a slower burning material than the outer explosives. The outer explosive would be detonated first, the shockwave spreading with great speed and hitting the lens, triggering an explosion there. These shockwaves would travel slower, and it was designed in a way that would create an almost perfect inwardly converging burn wave. This implosion wave would then crush the temper, uranium-238 in this case, crush the plutonium core to criticality and trigger the initiator. And boom! And the pressure created in this way is actually comparable to the pressure in the center of the Earth. Okay, disclaimer first. This section deals specifically with the early World War II era nuclear fission bombs. Very briefly, the three main damaging effects are the pressure or blast, thermal radiation or heat, and radioactivity fallout. The power of a nuclear bomb is usually expressed as a TNT equivalent. If a bomb has a yield of 1 kiloton of TNT, it releases as much energy as exploding 1000 tons of TNT. Typically, little boy bombs with around 60 kg of uranium had a yield of around 15 kilotons of TNT, and the Fat Man bombs with around 6 kg of plutonium had a yield of around 20 kilotons of TNT. For reference, 20 kilotons is about the mass of a warship, and the energy equivalent of 20 kilotons of TNT is taking a medium-sized lake and shooting it into low Earth orbit. The majority of the physical destruction is due to the pressure shockwave, knocking down buildings and other obstacles. The human body also has a limited tolerance to overpressure before it is simply crushed. The thermal energy output leads to burns and objects being set on fire. And while the temperature at the very center of the nuclear explosion is millions of degrees, this falls off quickly with distance. Only a few % of the energy were released as radioactivity, and this did the least amount of damage actually. And the reason for this is relatively simple. So if you were at a distance to get a lethal dose of radiation, you would already have been burned or crushed way before that. The total effect of radiation of the Hiroshima and Nagasaki bombings are debated to this day, because the long-term effects can be difficult to pinpoint and quantify. The most established estimate is that around 1,000 people died in the months and years after the bombings from long-term nuclear radiation effects, while around 100,000 were instantly killed due to blast and fire. This will sound surprisingly low to most people, as radioactivity is often demonized in popular culture, because it is invisible and difficult to grasp, so it seems very threatening and sinister. Which is true, of course, to some extent. It can be very dangerous, but most people have a completely wrong estimate of the numbers. For example, Hiroshima and Nagasaki are not some post-apocalyptic radioactive hellholes today, but regular cities with regular radiation levels. Also, what most people get wrong is that while the nuclear bombs were of course very destructive, a lot more people, almost 1 million, died from firebombing rather than from the nuclear attacks. The atomic bombs just did it in a singular event. And of course this created the threat of mass atomic bombing, which was tremendous and was a significant contribution to ending the war without having to invade Japan.